So now you can see some several examples. For example, if you take the first case here, you can see that average is 0 and standard deviation is 1. And then that's how the function looks like, the theoretical function looks like. You can see that indeed the peak is around 0, that's the average. Then you can see that we have about 3 minus 3 here, where the density is sort of not 0. Of course, it's not 0 also when it's 4 and 5, but it will be a very, very small number, okay? In the second case, we have the same average value at 0, but now standard deviation is equal to 2. And you can see that actually we have a sort of a stretch of this function. The total area is still equal to 1, but it's stretched because standard deviation is larger, so the variability is larger. And now instead of 3 and minus 3, you can see something like 6 and minus 6, so plus minus 2, plus minus 3 standard deviations, okay? Then in the final example, I have the same standard deviation as the previous case 2, but now the mean value is 1, and then you can see that the peak is not where the 0 anymore, it's where the 1, okay? So once again, average value shows you its most expected value, so it's a value with the highest density, and the standard deviation or variance, it's a measure of variability. It tells you how far the values can go from the average, and actually how fast will be a density decay when you go from the average in both directions. There is a very important empirical rule about how many standard deviations you can go from the average values. So if you take an interval 1 standard deviations of means, so you take the average plus minus 1 standard deviations, then you will have a total of 68.3% of the values inside, okay? So if you take, for example, if your average is 10 and standard deviation is 5, let's say 2, then 68.3% of the values will lie between 8 and 12. That's exactly 10 plus minus 2, right? Okay. Then if you take 2 standard deviations, it will give you 95.5%. So 95.5% of the values in our example will lie between 6 and 14, right? And that's exactly 2 standard deviations. Then if you take 3 standard deviations, you will have 99.7%. It's almost 100%. That's exactly why we saw this minus plus 3 in the previous slide, right? So 3 standard deviations gives you almost all values in your data, okay? And then quite often you need exactly 95% of the data. In this case, you have to take an interval slightly smaller than 2 standard deviations of means. It's exactly 196 standard deviations of means. So in normal distribution, if your data is distributed normally, 196 standard deviations of mean give you about 95% of it. Another very important statistic in normal distribution, it's called a standard score or z-score. Z-score, it's a standardized version for your values. It tells you how far your value is from the average in standard deviations, not in the same units as you measure the value, but in standard deviations, okay? To calculate a z-score, you just simply need to subtract from your value, you need to subtract the average, and then you divide it to standard deviation, okay? The operation to get the z-score, if you know x, it's called standardization. So you standardize your value, okay? And then here is an example. Let's say values are distributed normally with average 50 and standard deviation is equal to 10. What will be the z-score for these values? Okay, so let's take the first one. X is equal to 35. You can see that 35 is smaller than 50, but is it extreme value? Is it far from 50 or not? You can find it using z-score. So z will be 35 minus 50 and divided to standard deviation, which is 10. Then we have minus 15 divided to 10, which is minus 1.5. So it's minus 1.5, or by 1.5 standard deviations, it's smaller than the average. Is it far or not far? Well, you know that 2 standard deviations gives you 95% of the values, and this is 1.5, so it's within at least 95% of the most common values, okay? Then, for example, if you take 60, x equal to 60, the z-score will be 60 minus 50 divided to 10, which gives you 1. So it's one by 1 standard deviation larger than the mean, which is exactly in edge for 68.3% of the values. Okay.